we're going to be talking about some properties of liquids. All these properties have to do with intermolecular forces. First one is boiling point. Boiling point is the temperature at which a liquid boils and turns into a vapor. In order for a substance to boil, the intermolecular forces have to be overcome. All intermolecular forces have to be broken to go from a liquid to a gas. The stronger the attraction, or intermolecular force, the more energy is going to be needed to break that attraction. So the higher the boiling point. So make sure that you know higher IMF equals higher boiling point. We can see that in the picture over here. We have the trends across the periodic table. These three can hydrogen bond, and so that's why they have much higher boiling points than the other ones in their groups. When you're given data, you have to go off of the data. So here we have three substances and their boiling points, and it asks who has the strongest IMF. Well, the strongest IMF always has the highest boiling point. Therefore, I2 must have the strongest IMF. We don't have to go through and figure out what intermolecular force is in each of these substances, but if we did, we would say that H2O is hydrogen bonded, I2 can only LDF, and the last one is dipole-dipole as the strongest force. But remember that they also have LDF in the first, we have dipole-dipole and LDF. So although water has hydrogen bonded, dipole-dipole, and LDF, iodine's London dispersion forces are stronger than all three of water's attractions. We know that because it requires more energy to boil I2 than it does water, because iodine has so many electrons in comparison to the other two. When we don't have data, though, we're going to predict that ionic is going to be the strongest IMF, because that one we have to actually break bonds, and we're going to say that London is the weakest. Just like we saw in the previous example, though, London is not always the weakest, but without data, we cannot predict that. So for each of these, you're going to ID the IMF present, determine which is the stronger intermolecular force, and based on that, determine the higher the boiling point. You can use the abbreviations below to ID what type of force is broken. So let's do the first one together. This one starts with a metal, so that should be an ionic bond. For PCl3, you really should draw that one out. It has 26 valence electrons. So it has a lone pair on the central atom. Therefore, that's a polar substance, but it doesn't have hydrogen attached to N, O, or F, so that's going to be dipole-dipole. Well, ionic is stronger than dipole-dipole, so since it has the higher IMF, it should also have the higher boiling point. Go ahead and pause the video and try the rest of these on your own. Restart when you're done. The next one, drawing it out, it didn't have lone pairs, so that's nonpolar, so LDF. And then CH4 also is LDF. If you recall from our previous video or the previous lesson, we said that the more electrons, the higher the LDF. Well, PCl5 has way more electrons than CH4, so PCl5 we would expect to have stronger LDF. And if it has stronger LDF, we would expect it to require more energy to boil. The next one starts with a metal, so it has ionic bonds within and between it. Substance B also starts with a metal, so it also has ionic bond within and between it. Also, from the previous lesson, we said that for ionic, the higher the charges, the higher the ionic bond, or the stronger the ionic bond. Sodium's a +1, fluorine's a -1, so absolute value, multiplying those together, we get 1. Sodium's a +1, oxygen's a -2, so absolute value, multiplying those, we get 2. So Na2O, we'd expect to have a stronger ionic bond and therefore a higher boiling point. Neon is just a noble gas, so it only has London dispersion forces. Radon also only has London dispersion forces. So looking on the periodic table, radon and neon. Radon has 86 electrons while neon only has 10. So we would expect radon to have a higher boiling point and have stronger LDF. This next one was a little tricky. We had Br2, which is nonpolar, and water, which is polar. When we had a nonpolar and polar, that was dipole-induced dipole. And then HF is polar, as it has two atoms that are different. And we have hydrogen attached to F, so that can undergo hydrogen bonding. I am only listing the strongest IMF present, but remember that anything that is hydrogen bonded also has dipole-dipole and LDF, and anything that's dipole-dipole also has LDF. But again, we're just listing the strongest here. So the strongest IMF, or the higher IMF of the two, would be hydrogen bonding, so we would expect HF to have the higher IMF, and therefore higher boiling point. And finally, those last two are both polar because they have to have a lone pair on them. But water is hydrogen bonded, while HS is just dipole-dipole. Hydrogen bonding stronger than dipole-dipole attractions, so water has the higher IMF and therefore higher boiling point. So remember that these are just predictions on higher boiling point because we don't have data like the previous problem to know if a dipole is actually stronger than a London or hydrogen is stronger than a London, etc. Some other properties that you need to be familiar with is melting point. So just as energy is needed to overcome attractions for a substance to boil, energy is also going to be needed to melt a substance, just not as much energy. So the stronger the attractions, the higher that melting point is going to be. So if attractions between molecules are very strong, the molecules aren't going to have to slow down as much to freeze. So the higher the IMF, the higher the freezing point. So here we have 6 atoms, and so they're constantly moving around as a liquid. As they're moving, they form attractions and break attractions. As the temperature goes down, they're moving less and less, allowing them to form attractions and keep those attractions. If they have strong attractions, they're not having to slow down as much, aka lower the temperature as much for them to form these attractions and stay as a solid. So higher IMF, higher freezing point. So maybe it freezes at -5 degrees Celsius instead of -20 degrees Celsius. -20 doesn't have as strong of attractions, and so they have to slow down even more for it to freeze. Volatility is probably a new word for you. Volatility is the tendency of a liquid to evaporate at room temperature. Although it's a new word, you've seen volatility in action. If you've sprayed cologne on yourself or if you've used nail polish remover, both of those things evaporate very quickly. You spray the perfume on yourself and then it's gone in a matter of seconds. That's because those two liquids are very volatile. If attractions between molecules are strong, then the molecules will not turn into a gas very easily. So the stronger the IMF, the lower the volatility. So if you want a substance to be very volatile, you want weak attractions. Notice that this one has opposite IMF and the strength of the property. Here we have 3 tubes. Each of these tubes are showing you the pressure or how much of that liquid turned into a gas at the same temperature. So which of these 3 substances do we have the most gas? The blue, the green, or the orange? You said the orange, this one would be the most volatile. It's produced the most gas at room temperature. Viscosity is the measure of a liquid's resistance to flow. Again, you may have heard the word viscosity, you may not have, but you have seen viscosity if you've ever turned, let's say, a honey bottle or a syrup bottle upside down and try to squeeze some out. It's very viscous. It takes a long time for it to come out. So honey has a high viscosity while water pours very quickly. Water has a low viscosity. Of these three liquids shown here, if that ball bearing was dropped at the same time at the top, which substance has the greatest viscosity? If you said D, you are correct. Notice that it's gone very little in comparison to A in that same time frame. So liquid D must be thicker. It's taking a lot longer for the ball bearing to go down. So viscosity, sometimes I think of viscosity as thickness. It's not really thickness. It's the measure of a liquid's resistance to flow. But the more thick the liquid is, the more viscous it is. Glycerol is another substance that's very viscous. If you notice, it has attractions, which are hydrogen bonds, and this molecule is very complicated, meaning that it's stuck together and they get entangled with each other. So molecular complexity also leads to a higher viscosity because larger molecules can become entangled with each other. So higher IMF and higher complexity is going to lead to higher viscosity. You can also change viscosity of some liquids by heating and cooling them. Like honey, if you stuck that in the fridge, it'd become even more viscous. While you stuck it in the microwave and microwaved it a few seconds, its viscosity would lower and it'd pour quickly. Surface tension is the resistance of a liquid to an increase in its surface area. Again, you've seen these properties at play. You just may not have realized that they all have to do with the attractions between the molecules. The higher the IMF, the higher the surface tension. Here we see water beating up on a plant due to its surface tension. Not everything beads like that. Many liquids are going to just stay flat. But it's not going to want to spread out as much because there's attractions between those water molecules. The bug is able to walk on water because there's attractions at the surface between the water molecules, which allows the bug to put pressure on the surface and not fall through. And finally, capillary action. Capillary action is the spontaneous rising of a liquid in a narrow tube or an absorbent material. If you've ever stuck a paper towel in water, you're going to see that water travel up the paper towel. That's due to capillary action. It's also how nutrients and water go up a tree's roots is through capillary action. And finally, meniscus, when reading a burette or graduated cylinder, that meniscus is formed due to capillary action. We have cohesion and adhesive forces. Cohesion or cohesive forces are due to the intermolecular forces between the molecules. So water has an attraction with itself. So all this water is attracted to itself, but then it has adhesive forces between the glass and the water. Glass has silicon dioxide, and the water is attracted to the oxygen, or specifically the hydrogen in water is attracted to the oxygen in the silicon dioxide. And so it's trying to touch as much of that glass as possible, which is why it forms that meniscus. So higher IMF equals higher capillary action.